Henri Becquerel, on March 1st, 1896, discovered a mysterious form of radiation. He observed that the compound potassium uranyl sulfate continuously emitted invisible rays that could not be turned on or off. The mysterious radiation discovered on this date became known as radioactivity. Becquerel found that a radioactive source continuously emitted radiation at a fairly constant rate. This process was not affected by heat or by chemical solvents. He also found that when a radioactive material was brought near a charged electroscope, it ionized the air, and excess charges from the electroscope leads were quickly neutralized, so discharging the electroscope. Pierre and Marie Curie applied this principle to design an instrument which they used to measure the strength of a radioactive source. The power supply caused one plate to acquire a charge, while the other plate acquired the opposite charge. Because of the gap between the two plates, there was normally no current flow, and the meter registered zero. The Curies reasoned that when a radioactive sample is placed near the plates, the radiation given off by the source would affect the molecules of the air found between the plates. For example, when a specific atom interacts with radiation, an electron may be knocked out of the atom, leaving behind a positively charged ion. So, between the plates of the apparatus, many charged particles are formed. The negatively charged plate begins to lose electrons because they are attracted to the ions. Meanwhile, at the positive plate, free electrons are attracted. These electrons enter the positive plate. The resulting flow of charges through the air permits a current to flow through the circuit. The stronger the source of radiation, the greater the current flow. In 1899, Ernest Rutherford used this principle to examine the radiation given off by uranium. He placed very thin aluminum foil absorbers near a uranium sample and watched the meter to see if the reading on the detector changed. He found that the reading dropped rapidly as the first few sheets were added, but declined at a much lower rate as more sheets were added. The graph shows that the radiation drops dramatically sheet by sheet until after 4 sheets it levels out. From these results, Rutherford concluded that the radioactive source must be emitting at least 2 types of radiation. One had very little penetrating ability and was completely absorbed by several sheets of aluminum foil. He called this alpha radiation. The second type was able to penetrate a much greater thickness of aluminum foil. He called this beta radiation. Within a year, the French physicist Paul Villard showed that there was a third type of radiation, which had a much greater penetrating power than beta. It came to be known as gamma radiation. Further experimentation revealed that alpha, beta, and gamma radiation differ in other ways. A radioactive source, enclosed in lead shielding, with a single opening on one side, produces a beam of radiation. When a magnetic field was placed near the source, the alpha radiation bent slightly in one direction. The beta radiation bent considerably in the other direction. The gamma radiation was not affected but continued in a straight line. has showed that alpha and beta radiation consist of particles that have opposite charge. Further work carefully measured the deflection of beta particles and compared the results to those produced when a beam of electrons interacted with a magnetic field and deflected in the same way. Eventually, it was concluded that the beta particles were identical to electrons. These beta particles travel at high speeds, which in some cases approach the speed of light. What about alpha particles? Well, Ernest Rutherford showed that alpha particles normally travel much more slowly. Each alpha particle is identical to the nucleus of a helium atom and has twice the charge of a beta particle. They're also heavyweights compared to beta particles. Each has a mass about 7,200 times that of a beta. Gamma radiation was eventually shown to be like visible light in other forms of electromagnetic radiation. It has no charge or mass and travels at the speed of light. In 1911, the Scottish physicist Charles Wilson developed an apparatus which gave direct visual evidence of radiation. The modern version consists of a block of dry ice on which is set a plastic cylinder. A ring of absorbent material inside the dish is saturated with alcohol. When a radioactive source is inserted in an opening in the cylinder, then the apparatus is illuminated by a light source. Tiny vapor trails soon become visible. What creates these trails? Well, the liquid alcohol evaporates to form a vapor, which is cooled by the dry ice. A particle of dust, or even an ion, can cause vapor molecules to condense into a visible droplet of liquid alcohol. A single atom becomes ionized when radiation interacts with it to strip away electrons. Because it is so large, the alpha particles make many of these collisions. Droplets of alcohol condense about each ion to leave a well-defined track. The alpha particle loses all of its kinetic energy through many collisions in only a few centimeters. Its track is relatively short and thick. On the other hand, the smaller, faster beta particle travels farther between collisions, and as a result leaves a track that is long and thin. Gamma rays, which are not particles, travel at the speed of light and only infrequently interact with atoms to form ions. As a result, they leave a trail in the cloud chamber which is long and difficult to see. All in all, researchers were doing a fine job of exploring and describing different kinds of radiation. But what was causing this radiation? What was going on inside matter itself?